Hello everyone, welcome back to a new lecture on the topic zero crossing detection as a part of the course Signal Processing Algorithms and Architecture. I am Dr. Anirban Dasgupta, your instructor, and let's get started. So, time domain signal processing, this is a summarization of the topics. So, we already have discussed time shifting and scaling, amplitude shifting and scaling, modulation, correlation and convolution. So, today we are going to start the topic on zero crossing detection, and in the subsequent lecture we will be talking about peak detection, envelope detection, signal smoothing and pattern matching. So, what is a zero crossing? So, zero crossing is, as the name suggests, is a point where the sign of the signal changes. For example, the signal value can change from a positive to a negative and vice versa. So, this is represented on the time axis as a zero value, as you can see in the graph. So, these points where the signal value touches 0 and switches the sign. So, this looks very straightforward. So, now that signal was kind of a continuous time signal. Now, let us see what happens in a discrete time signal. So, here we have specific values at specific integer indices. Now, here we see that in this case the signal value is rarely 0 at a zero crossing, but we can see that in consecutive samples like this sample and this sample, or this sample and this sample, the sign of the amplitude changes. So, in simple words, a zero crossing can be either an exact value of n at the point where the signal value is 0 and the other sides have different signs, or the zero crossing can lie in between some two integer indices like n and n minus 1, where the zero crossing is somewhere in between. Now, technically, as I said, a signal is a physical phenomena and a zero crossing may indicate some event in the signal. So, we want to capture it in the original time sequence rather than the sampled signal. So, we need to estimate that value of n and then finally map it to the analog time axis t. And as I said, it can be a specific integer value of n or it can lie between two integer values. So, let us understand some zero crossing detection terminology. And the first is the zero crossing point. And as I said, this is the point in the signal where the signal value changes from either positive to negative or vice versa. And depending on the zero crossing points, how many such points occur in unit time is called the zero crossing rate. And finally, we have something called a threshold. So, threshold, consider that this is a small value near 0, some value like epsilon, which is there to ignore small fluctuations of the signal, because such fluctuations often occur in real signals because of noise, and these are often called noise induced false zero crossings. So, to reduce that effect, thresholding technique is used, which we will discuss. So, what is the need for zero crossing detection? The first is frequency estimation. Like if you see a sine wave and if I tell you what is the frequency, how will you do it? So, you will basically see how many zero crossings are there or exactly where the zero crossings are occurring, and based on that you can actually find the time period or the fundamental frequency of that signal. In speech processing, zero crossing detection is of paramount use. It is often used to distinguish different segments of speech signal. Signal classification is another application where the zero crossing detection is used to classify various forms of signals. Then edge detection. Now, this is also a very important application of zero crossing detection specifically in image processing where edges are found using the concepts of zero crossings. So, considering these applications, what are the real problems in zero crossings? So, in the above figure you see that this is a beautiful clear sine wave and it is very easy to find the zero crossing, even a school student can do it easily. But if you are given a signal like this, which is often the real world case, so real world signals are not so clean as the above figure. So, how do we find the zero crossings in such a case? Because here we see that there are a lot of noisy regions which make that believe that these are zero crossings, but actually they are just noise induced zero crossings and it does not truly signify any event in the signal. So, what is the concept? What should be the naive approach of detecting? So, let us try to define the cases where the zero crossing can happen, and based on that we will try to formulate the algorithms. So, as I said that zero crossings are detected when the signal sign changes between two consecutive sample points. So, suppose we have a discrete time signal x of n and say for a specific value of n, x of n is 0, and also we check that the previous sample and the remaining sample, like the previous sample and the other sample. So, these two samples are of opposite polarity. So, if two successive points are there, for example, as I said in the last case, so this is my n minus 1 and this is my n, then in this case this zero crossing will be by checking the polarity of successive samples. But if a specific point at n the signal is 0, then we will check the previous sample and the next sample. And this is the sine function which is having a value of 1 if x is positive and a value of 0 if x is negative. So, if there are p consecutive zero signal values, like the values are say zeros for say some p times, and then you have one negative value and on the other hand one positive value. So, you have to check if consecutive p values are having zeros, then the previous sample and the next sample apart from this group of zeros should be of different polarities. And finally, once we get the count of these zero crossings, we can easily calculate the zero crossing rate. So, these are the total number of zero crossings in the signal. What we will do is we will divide by NTS. Why NTS? Because these are the crossings in n number of samples, and if we divide by TS we get that per unit second. So, this will give me number of zero crossings per second. So, let us try to demonstrate each of these cases pictorially. So, the first case is that the n is between two consecutive samples n minus 1 and n minus 2, and here we check the signs are different, and this is one case. So, here we see that at n equals to 2 the signal is positive and at n equals to 3 the signal is negative. So, the 0 will be somewhere in between these two samples. The second case is exactly we have a value where my signal value is 0. So, we check for one value before that point, that is n equals to 2, and after that point, that is n equals to 4, and see whether these two are of different polarities. If they are of same polarity, like say this is also positive, so this is just touching 0, it is not crossing 0. And the third case is that I have some p number of values, like here p is 4. So, 4 values are having zeros. So, I check the value previous to this group which is at n equals to 2, which is positive, and a value after this group which is n equals to 7, which is negative, and hence we can say there is a zero crossing. So, now let us try to understand the detection methods or detection algorithms. So, typically there are a lot of algorithms available, and mostly there are very few books which actually discuss these concepts. I have mostly taken this from research papers, and the methods include dot product methods, the method of interpolation, windowing method, and hysteresis method. So, quickly we will discuss all these methods. The first is a dot product method, and again it is a very naive algorithm where, as I said in the definition, that the two successive samples, and this is mostly the case in practice, because in practice you do not get the signal value to be exactly 0. It can be some small positive and the other end can be small negative. So, for this case we will do the main analysis, but you are free to select the other cases also, but this is the most occurring case. And in this we see that, so if one value is positive and if one other value is negative, what is the best way? So, just multiply them. So, that is why it is called a dot product method. So, just multiply them and check whether it is negative. So, if this is negative, that means there is a 0 crossing. So, this should be just less than 0. But again, if you consider this equals to 0 also, it actually takes care of that case where exactly n is at x of n, at n x of n equals to 0. So, this is typically an indication whether there is a 0 crossing present in the signal or not. And once you have detected the 0 crossing, the next task is to find where is the 0 crossing, and that is also evident by this formula. But wait a minute. So, I know that at n and at n minus 1 the product is negative. So, which means that my 0 crossing is typically lying in between these two samples, but I need to find that value where it is lying, and more precisely I want to know in the analog time axis where that 0 crossing is happening. So, what do we do? So, in this case we can take the average. So, average of n minus 1 and n will be n minus 0.5 or n minus half. So, this is typically taken as the estimated 0 crossing value. Now, you might be wondering that this is not an integer value and how is it possible? Now, since we are mapping to analog, so ultimately when we multiply with the sampling time Ts, it will make sense. So, now about the complexity, since this is an algorithm. So, each comparison, let us say it is a constant time operation. So, there will be n minus 1 such comparisons for a signal of length n, because we are comparing successive samples. So, hence we can say the complexity of this algorithm is O of n. So, let us take an illustration of this problem. So, we have a small signal, small just to show for illustration purposes, and we have the values as 3, 4, 5, negative 6 and negative 7, and clearly we know that this is the region where my 0 crossing will lie. So, what we do, we take the index pairs like this, and these are the signal values corresponding to the index pairs. We find the dot product, which is nothing but the multiplication, and basically we see that at this point or at between these two samples the value is negative, and which means that yes, there is a 0 crossing detected between the samples at 2 and 3. And as I said that in this method we will take the unbiased estimate as the midway, which is 2.5, and now we can map that based on the sampling time. Now, you may argue that the middle point may not be a very good estimate, like consider a 0 crossing where the signal value at n minus 1 is a value very small, which is a minus 2, and at n it is having a very high value, say plus 8. So, you will see that the portion should be very much closer to minus 2 and very much far away from plus 8. So, what is this? This is a linear interpolation instead of taking the midpoint, and this is giving me a reasonably better accurate of the zero crossing point. So, this is the new algorithm which is zero crossing detection with interpolation. So, in this the only change is that I am using the same algorithm for detecting whether zero crossing is there or not, but for marking the zero crossing, instead of taking the midway, I will use this linear interpolation formula, which is n minus 1 minus x of n minus 1 divided by x of n minus x of n minus 1, and this you can easily derive by using this diagram. And using this we will take the same example, but here, so we have the points x of n minus 1 as 2 and x of n as 3. So, we will use the interpolation formula and we find that the value is 2.45, which is different from the previous algorithm 2.5, and this is keeping the fact that 5 and negative 6 are different heights. So, this is the algorithm and we will compare the complexity. So, as you know that this comparison will take O of n time like the same dot product method. So, interpolation, of course, you will do the interpolation only when these zero crossings are detected, but if say we have a very noisy zigzag signal where every pair of points has a say zero crossing, so still we get the worst case to be O of n. So, overall we can say that the complexity will be O of n, linear time complexity, and this is what I was referring to in the zero crossing detection with interpolation. So, since this value is having a higher height and this value is having a lower height, so this zero crossing is not exactly midway, but somewhere biased towards the lower height sample. Now, these two algorithms look pretty naive in nature and easy to understand, but there are some shortcomings, such as noise induced false zero crossing. As I said that there will be lot of like these signals where the zero crossings may appear by the formula, but they are typically because of noise. Another is interpolation error, like we discussed that these 2 points. So, we will typically do a linear interpolation, but actual signal may be too curvy in nature, and a better interpolation method can be a quadratic or a higher order polynomial. You never know, like if it was originally a sine, maybe if the spacing is large, a linear interpolation may not give you the exact precise point. Then multiple zero crossings between 2 points. Now, this is not a problem with the algorithm, rather it is a problem of undersampling, and this is violating Nyquist rate. Like this says that if there are some oscillatory nature, so we will miss some zero crossings, but this is natural because then this is a high frequency signal and we have probably sampled it at lower frequency, and that is why we are missing these zero crossings. So, this is a undersampling problem, this is an aliasing problem. So, what are the other issues? So, the boundary issues, like we have the boundary of a signal and we cannot apply that in the boundary, because we have to see that we have to neglect the boundary pixels, because we cannot find an n minus 1 for the first sample and n plus 1 for the last sample. So, in that case often the boundary is neglected and the boundary pixel may be a zero crossing, you never know. So, how to solve these issues? So, one is noise induced false zero crossings, which can be removed by smoothing or filtering the signal before applying this algorithm. Now, smoothing techniques we will discuss in subsequent lectures, but if you are facing this problem, you can go by smoothing the signal first before applying this zero crossing detection algorithm. Interpolation errors, as I said that this is you can solve it if you are like very much interested in that kind of fine precision, then probably you may consider higher order interpolation like quadratic or cubic splines. But if you are okay with a small error in precision, then linear is good enough. Multiple zero crossings between 2 points, as I said, is a sampling problem. So, you should use a higher sampling frequency at the sampling time itself to get a very precise, and do not miss any zero crossings, specifically in high frequency signals. For the boundary issues, now one way is to use mirroring. So, you can extend the signal by mirroring the last few or the first few values, so that the boundary issues are handled carefully. Now, here zero padding may not be a good way to solve it, because in this case zero padding will not help you to get whether there was any actual zero crossing or not, but mirroring might get. Of course, mirroring is also a very accurate technique, but this will ensure that your boundary values are handled. Now, some signals may have some switching nature. Switching nature means, so the signal values are say having a trend like this. So, this is often called a non-stationary signal, where the signal mean is deviating from the baseline. This is also very common in biomedical signals, and it is called baseline wander. So, here instead of doing globally, what you can do is you can do a windowed zero crossing detection. So, you can take small windows, then you normalize the signal and then apply the zero crossing methods. So, the algorithm is you have to divide the signal into either overlapping or non-overlapping windows. Now, what to use will be dependent on your application, and usually the naive method is to use fixed size windows, and then for each window, so each window behaves like a sub signal. So, in each signal you apply the methods discussed earlier, and then you can combine the results from each window, and this method will give you the zero crossings. So, if we talk about the time complexity, so dividing the signal into windows will take O of n times, because you are assigning each point to a specific window, and considering the windows are non-overlapping, you get O of n times, because ultimately you have n number of sample points, and then you want to aggregate also, you have to check O of n. So, O of n, O of n, O of n is a complexity of O of n. So, although this method is better for non-stationary signals, but there are issues like the window size. So, what window size you need to select such that you get a very nice accurate result. So, one way is to have dynamically changing window size, and that is also a research problem, and this is specific to the signal which you are trying to analyze. Then overlapping window is also a concern, like if you have very high amount of overlap, say 90% overlap, then the computations will be pretty high. Then it won't be n of n, that overlapping part, it might become nearly n square, because if you are using 90% overlapped windows. If you are using less overlap like 25% or 0% non-overlapping windows, then also you may miss some portions. So, what percentage of overlap you should take is again a critical issue. And windowing artifact is again that boundary conditions are appearing here, and here since you have a window, so each window will have a boundary problem and it will require a boundary check. So, this is one result with the windowed zero crossing. Now, of course, this signal is not having any trend, but still you can see that we are able to detect most of the zero crossings. Of course, in some regions we have spurious zero crossings because of some fluctuations in the signal, which is typically solved using the method which is called the hysteresis method. So, in hysteresis, so if you see there is a zero line, this is the time axis. You say t or n, anything you say doesn't really matter. So, you see that now here technically I would say this is my actual zero crossing or prominent zero crossing, but these are kind of noise induced zero crossings. So, how to solve this? So, we can have two lines which I call thresholds. One is the upper threshold, which is for the positive cycle, and the lower threshold, which is for the negative cycle. So, typically these two values are taken to be equal, but there is no hard and fast rule. You can take your own thresholds. So, in this method you can actually remove the noise induced zero crossings by properly selecting the threshold value. And all these algorithms, as I have explained, is solving a specific problem. So, which problem you are having, based on that you are free to select your algorithm, and you can devise your own algorithm which can be a combination of all these steps. So, the algorithm is, first I will assign the zero crossing state to 0, that means initially there are no zero crossings, and then we will check whether the signal exceeds the high threshold, which is a mark of a positive crossing, and if the signal falls below a like lower threshold, then it is a sign of a negative zero crossing, and then we will just check for the conditions like in the dot product case. And again this is a n complexity, because we are just checking or comparing each sample against the thresholds. So, possibly you are having two comparisons for each sample, for the high threshold and for the low threshold. So, this is all from zero crossing detection. Thank you. We will return with the new topics.